Question B is actually very simple to answer. Let's answer that one first. We are told that there is a potential difference between a top and a bottom plate of V. So it's a parallel plate capacitor. The assumption is made that the electric field between the plates is of uniform, is a uniform electric field. So we treat it as if they are, very large plates and we are very close to them. That means that the electric field being uniform says the potential difference has to be equal to E times D, so the electric field between the plates is V over D. Now we proved this on Friday by doing it through integration, if you guys recall, but we don't have to. We know it's a constant electric field. Now, that gives us the electric field, but they asked for the force on the top plate from the bottom plate. And that would be question A, but I think using this will make it easier because the force has to be equal to Q times E. Now, we can't use Q in our answer, but we can use other things that we have here in our answer, so let's do so. Capacitance is equal to A epsilon naught over D, and by definition, charge equals C times V. So the charge here is, well, A epsilon naught V over D. So if I want to find the force on the top plate from the bottom plate, I could do force equals Q, which is A epsilon naught V over D, times E, which is V over D. And that means A epsilon naught V squared over D squared. Now we did this two different ways on Friday, but it might not have been super clear. We did it this way, and we did it by actually integrating from one plate to the next. So both of those would work. This is clearly the simpler way to do it. All right. So we apply a force to pull the plates apart, and we increase the separation to 2D. Well, the potential difference doesn't change because there's an applied potential difference. It's staying the same. So that's the first question we'll say. So V is the same. Now, if we had isolated the capacitor and done this, I'm not sure V would have stayed the same. But because we are staying connected to the potential difference, V stays the same. The capacitance, on the other hand, goes down by a factor of 2 because we're going from that to this. This will definitely affect the charge then because we have less capacitance, we're going to have less charge. Q equals CV. So I want to do this two different ways. First, the original amount of charge, we'll say Q naught, is A epsilon naught over D times V. Our new charge, we'll say Qn, is equal to A epsilon naught over 2D times V. So is it clear that that equals half of Q naught? That all good? All right. So the original potential energy was 1/2 Q naught, I'm sorry, 1/2, let's just do it this way, 1/2 CV squared. That's the original amount of energy. The new energy is 1/2 times 1/2 C V squared. That all good? So we now have half the amount of our original energy. All right, the potential stayed the same. Any question about any of these choices? All right, so those are all those answers: energy, charge, electric potential. Was there anything else in that list of things? All right, so we did positive work to separate the plates because the total amount of energy went down, and work equals the change in potential energy. And now we have to do the whole thing over again, this time for an isolated system. So if it's an isolated system, the electric potential is not going to stay the same. However, if it's an isolated system, something else will stay the same. What will that have to be? It'll have to be the charge. Yeah, if it's an isolated system, there's no place for the charge to go. The charge will remain on the plates. So we'll start way back at the beginning and take all this stuff out of here. It's gonna make a bit of a difference. Some things won't change, but some things will. So let's start with question B and A. They stay the same because this isn't before we've made any change to anything. So we're just talking about what the force is and what the electric field is, and that's all still the same because no change has happened to the capacitor. Does that make sense to all of you? It's still isolated. These are still going to be the forces necessary. This is still going to be the forces necessary. This is still going to be the electric field between the plates. However, when I begin to separate them, then things start to happen. So let's consider the things that are going to happen. The charge stays the same, but the capacitance is still cut in half. So the capacitance, the original capacitance is A or epsilon naught D. Our new capacitance is A epsilon naught over 2D. So our new capacitance is half of the old capacitance. Q stays the same. So when I look at Q equals CV, it might be better to write this as V equals Q over C. Because Q is going to stay the same, but V is going to change. So now we can find out how V changes by seeing how C changes. And it looks like to me that if this is the original potential based on the original charge and the original capacitance, that my new potential is going to be the original charge divided by C naught over 2. And that looks to be like 2 times the original potential. Any question about that? Alrighty. Let's move on. So we've done capacitance, we've done charge, we've done potential. So the original energy was 1/2. I think I want the version that's got charge and capacitance in it. That's the one I want. So which one is that one? Yes, ma'am. Q squared over 2C. There we go. Because Q stays the same. So my original amount of energy is just that. My new amount of energy is going to be 1/2 Q naught squared over C naught over 2. Well, this looks to be like 2 times the original amount of energy. Do all of you agree with that? Okay. So the change in U has to be 2 U naught minus U naught or U naught. How much work is done? Work is equal to minus change in potential energy, so minus U naught. Ta-da. And you should probably, I mean, really, I shouldn't put U naught there. I should put something else, like maybe put in terms of the charge, maybe put in terms of the capacity. I mean, we're given physical parameters, so I should probably put in terms of the physical parameters. But I think the intent of this problem is for you to see how the various things change under the 2 circumstances. So I think this was reasonable. All righty. So I guess I'm speaking. Let me make sure we're all together on this. We all understand that this part was pretty straightforward, right? They gave us some values to use, and we just came up with the capacitance based on those values. It then said we have 2 different dielectrics. We have to fill half of the space with one dielectric and half of the space with the other dielectric. This is a way to do that. Now, you would not have known that you could treat these like 2 different capacitors in series. So that's something new. I mean, truthfully, it's probably in a chapter, but it's not always in every book. So now you do know that. I suspect that's enough information for you to actually do the problem. But I'm still going to finish off the one here, and then I want to talk about the other ways that we could have filled this space. I know. They're both asleep. It's really frustrating. I think they're taking up valuable front row space too. And I find that just so disrespectful. I can't really express it in words. But hey, it's the way it goes. The top one is 4. I'm going to multiply by 4, so that's going to be 16 e to the 6th. And epsilon naught, so that would be the capacitance for the red capacitor. Any question about that? All right. So the blue capacitor, similarly, A epsilon naught kappa is 4 over 1/2 d. And that equals 2 epsilon naught times 4 over 0.25, 25 e to the negative 6th. 8 times 4, 32. E to the 6th, epsilon naught. So those are two capacitors. But they are in series, so I have to use the rules for series. So 1 over 16 e to the 6th epsilon naught plus 1 over 32 e to the 6th epsilon naught equals 1 over c total. I mean, you get common denominators, right? Just 2 over 32. This is just arithmetic. So 3 over 32 e to the 6th epsilon naught equals 1 over ct. So c total equals 32/3 e to the 6th epsilon naught. There it is. So about 10 e to the 6th. Am I right there? Is something wrong with my arithmetic? I went fast because I was frustrated.
Why is there 2 over the 32 e to the 6th?
I got common denominators. It was 1 over 16. All good? So there's another way you could do it, right? There's a different way to fill the space. Again, there's an infinite number of ways to fill the space, but I'm thinking in my head there's probably only one other problem that we could probably reasonably do. And that would be something that look like this. I'm trying to draw it nice and symmetrical. So I'd put the capacitor on this half and a capacitor on this half. Now, if we layered the dielectrics and that meant they were in series, what do you think here? Parallel. So it's the same problem, but they're in parallel now. But remember, in this case, the separation distance is the same, but now half the area, right? Do you want me to complete this problem, or do you feel like you guys could successfully do this one? I think once you understand about series and parallel for this stuff, this isn't too terrible. But that's what you have to do. You know, and Hans, I was a little short. Yeah, there are reasons why they would do it this way. One of them could be, and maybe not this way, this one I wouldn't understand, but the other one I think might be just a manufacturing issue. Not every kind of metal can be etched with the same kind of reactant to produce a substrate on the metal. And so there are plenty of capacitors that use two different kinds of metals. They're electrolytic capacitors. And so they'll oxidize one plate, but they might do a different process on the other plate, producing two different dielectrics on each plate. Then they slap them together. And when you calculate your total, it comes to something like that. So that's one reason why it might be that way. I can't imagine any reason why side-by-side would be necessary for any purpose except for fun times here, you know. But I don't think that this is necessarily a realistic way to do it. But the layering of the dielectric, that does happen. All right, so this is the first FU. And so, question A, close S1. Aww. I guess we won't be going over this problem. This part's easy though, right? This is just gonna be Q equals CV. All right.